Hello everyone, my name is Kodchakorn Simalaota. I'm a PhD student at the University of Tsukuba and a member of Magnetic and Spintronic Materials Research Center at NIMS. So today I would like to talk about for principal prediction of high magnetoresistance in CPP-GMR device with half metallic cobalt, iron, gallium, germanium electrode. So let's begin with the introduction. So nowadays, one of the most common problems in our digital society is increasing the capacity needed to store the new demand, as shown here. So to solve this problem, increasing data storage density is a key technology supporting our society. In practice, improving aerial recording density of solid-state drive or SSD and hard disk drive or HDD is needed in present. However, the HDD is the representation device for magnetic recording, which had three advantages of large capacity, low cost, and non-volatility. Recently, Seagate launched a new high-capacity hard disk drive with 30 TB, which underscores the challenge of developing very small and efficient lead head. For the next generation of lead head in hard disk drive, over 2 terabit per inch square, CPP-GMR device is one of the most promising candidates. So, supporting by recent research published this year, has shown the improvement in CPP-GMR lead head sensor performance using bilayer electrodes, as shown here. This reflects on the ongoing challenge of developing CPP-GMR lead head sensor in material science. So what is the CPP-GMR device? CPP-GMR stands for current perpendicular to plane giant magnetoresistance. This device is a type of magnetic sensor that relies on the giant magnetoresistance effects, which is a phenomena where the electrical resistance changes in an applied magnetic field. The device consists of two ferromagnetic layers separated by non-magnetic spacer, with the electrical current flowing perpendicularly to the plane of the device structure. When the magnetization direction in ferromagnetic layer are anti-parallel, the total resistance in this state is high, otherwise is low. The difference in resistance between these two states we know as the magnetoresistance ratio or MR ratio, which can be described by this equation. So in this device, the key advantage is the small resistance area product, which is beneficial for creating small lead head in hard disk drive. However, the significant challenge is the device low MR ratio due to its metallic nature. Consequently, improving the MR ratio is critical for advancing lead head application. So how the MR ratio is determined in CPP-GMR? It is determined using the two current series resistor model, which can be described by this equation. There are two intrinsic factors related to spin-dependent electron scattering that influence the MR ratio. First, beta is bulk spin asymmetry coefficient. Second is gamma, is the interfacial spin asymmetry coefficient at the interface. So from this equation, it is evident that the MR output can be enhanced not only by increasing beta, but also improving gamma. So the key question becomes how to enhance beta and gamma parameters. Beta can be maximized by using half metallic materials at the ferromagnetic layer, such as cobalt, iron, gallium, germanium, or CFGG, because it provides ideally 100% of spin polarization at the Fermi level. Gamma is enhanced by reducing the majority spin interface resistance in the parameterization configuration, which can be described by this equation. Combining these two factors lead to improve the MR ratio, as shown by this relationship. Then to validate this theoretical concept, the correlation between theoretical IA value and experimental GMR at room temperature was investigated in previous study, as shown here. So this correlation shows that reducing the majority spin interface resistance increase the MR ratio in the experimental result. And for the previous study, they found that using the AG spacer with the CFGG electrode provide a high MR ratio compared with the other single crystal spacer. Consequently, the aim of this research is tied to explore new non-magnetic spacer materials, focusing on copper-based binary alloy, because what kind of this material, a small spin orbit coupling and large conductivity are expected. So by selecting the non-ferromagnetic copper X spacer materials, we aim to reduce the majority spin interface resistance compared to the traditional AG spacer. For the material candidate screening process, we focus on elements within the lead rectangular, as shown here, which includes allow 45 copper X system. For the initial screening of materials, we use the Open Quantum Material Database to select the system based on their stability, as indicated by negative formation energy and the lattice mismatch with the CPP-GMR electrodes less than 10%. So out of 45 systems, 31 meet this criteria. However, today I would like to share my result of the transport calculation for 19 special materials with B2 type and L12 type structure, and we will compare our calculation result with the AG special materials. Computational method, our calculation based on density functional theory. So the ballistic conductance was calculated using the Lander formula. All the magnetic junction were constructed in the tetragonal configuration with the in-plane lattice parameter fixed as allowed for 0.1 angstrom, as shown here. So the first supercell structure is for the AG special materials, where the interfacial termination depends on the electrode materials. There are three possible interfacial terminations, which are FEGE, CO, and FGEGA termination. For the copper X special materials, the interfacial termination depend on their structure. For the copper and X termination is for the B2 type structure. So copper and copper X termination for L12 type structure. Result and discussion, we first calculated the formation energy and the majority spin conductance at the interface. So this slide shows the formation energy in the first law and the majority spin conductance in the second law, which is special materials at the FEGA termination, which is the most stable interfacial termination compared to the others. So the results are compared with the AG special and indicated by the back dashed line. The first column is the result for B2 type structure with copper and X termination, and for the second column is the result for L12 type structure with copper and copper X termination. For the formation energy, a more negative formation energy indicates a greater stability. So by the overall mode, the copper X special material provide a greater structural stability compared to the when we using the AG special. So for the conductance, the copper X special material that provide a higher conductance compared to the AG special are highlighted as the potential candidate for achieving a higher MR ratio as indicated by the red rectangle here. Then the interface resistance area product as a function of conductance was investigated with the potential special material highlighted from the previous slide. I show with the different termination as shown here. So you can see that the copper zinc special material provide the lowest RA value, as indicating is at the most optimal candidate for the half metallic CPP-GMR electrodes. Specifically, it provides approximately 30% RA reduction compared to the AG special for the copper termination and allow 25% RA reduction for zinc termination. So then the analysis of the Fermi surface matching comparing between using AG special and copper zinc with the copper termination, which is the more stable interface, will be presented on the next slide. So this is the 2D images in plane wave vector K-parallel dependence in the balance zone for AG special and copper zinc special. The yellow color represents the high conductance. So for the copper zinc special, the highly conducting region spread over almost the entire region. On the other hand, for the AG special, the lower conducting region occur around the edge of the balance zone. Then to understand orbital contribution, the Fermi surface of bound material will analyze based on SP and D orbital as shown here. So for the conducting region for the AG special is mainly due to the hybridization between D states of the CPP-GMR electrode and P state of the AG special occur around the edge of the balance zone. For the copper zinc special, the highly conducting region results from two factors. First is the hybridization between B and D states of the CPP-GMR electrode and the S states of the copper zinc allow the gamma point. Second is the hybridization between D states of the CFG electrode and P states of the copper zinc along the diagonal of the valence zone. It is evident that the S states of the copper zinc spacer occur along the gamma points, play a crucial role in enhancing conductance, making it the key to improving the performance. So conclusion, so in this result, we can predict or identify several special material for CFG electrode that significantly boost the MR ratio in CPP-GMR device compared to the traditional AG special as determined by for bespoke calculation as shown here. And copper zinc special material stand out as the most optimal candidate for the half-metallic CFG electrodes because a good Fermi surface matching with not only the s orbital allow the gamma point, but also p orbital along the diagonal of the valence zone. And it also have the superior structural stability compared to the AG spacer. Thank you for your kind attention.
Thank you for the interesting presentation. Now it's open for the discussion.
Hello, can you hear me?
Yes.
Okay, may I know that as compared to CPP-GMR, how is CPP-GMR compared in terms of performance of any device?
How the CPP-GMR compare?
Yeah.
Pardon? Your question is how the CPP-GMR compare with?
No, I mean, I just wanted to know that generally it is seen that CPP-GMR gives out a higher MR ratio as compared to CPP-GMR.
CPP-GMR and TMR, right? Yeah. Actually, for the TMR, the spacer is made from the insulator, right?
Yes.
Materials. So it's make like a very high MR ratio, but the critical disadvantage is because we need a very small lead in hard drive, but because of the limit of the making the size of the device, so TMR cannot support in this kind of application. So yeah, that is the difference why we need the CPP-GMR because of that I mentioned the advantage is a small distance area product that can make the small retard. Yes.
And one more small thing is there that if I choose CPP-GMR configuration in which the tunnel barrier layer in between layer, that is a magnetic insulator rather than a non-magnetic insulator. So, and how does it affect the performance of the device?
You mean the difference between non-ferrometric layer and insulator? How?
No, actually in TMR, basically we have been in literature people are using a non-magnetic insulating layer in between the ferromagnetic electrodes. But if I use any magnetic insulator instead of non-magnetic, how does it affect the performance of my device?
If you use the magnetic materials, which mean you actually the purpose of when we use the ferrometric layer, we try to use the half metallic materials, like because we need the high spin polarization to keep the spin orientation. So when you switch the magnetization, if you have the spacer, that magnetic material will be disturbed the spin moment. When we transfer the spin accumulation from one side to the other side. Yeah, this is maybe affect the MR ratio. Yeah, maybe reduce the MR ratio. Yeah, this is my understanding.
Thank you.
Thank you, Simalaota, for your wonderful presentation. There is a question in the chat box, but I will request to discuss more detail about the question in the gather town. So you can find the question here. So thank you.